In this video, we'll be looking at differentials. First, the definition. Let y equal f of x be a differentiable function on an open interval containing x. The differential of y, called dy, is defined as dy equals f prime of x dx. So we're familiar with delta x and delta y as the change in x and the change in y. We use dx to represent a very, very small change in x, or an approximate change in x. And dy is a very, very small change in y. So why use dx and dy instead of delta x and delta y? Let's consider the function f of x equal x squared. The line tangent to that function at the point 2, 4 has the equation y equal 4x minus 4. Let's look at the graphs of these two functions and see what happens. Now this is both of our functions graphed on the same coordinate plane. What we want to do is zoom in on the point 2, 4. We're almost to the point where we can't tell the difference between the curve and the line. Now let's zoom in one more time, and you can see that we can't tell the difference between the tangent line and the curve. So the reason for using dx and dy instead of delta x and delta y is because if we have very, very small changes in x and y, you can use the linear approximation for the curve instead of the actual curve itself. So let's do a linear approximation example. Our problem is find the tangent line approximation, we'll call it t of x, at the point 0, 1 to the graph of the function f of x equal 1 plus 2 sine x. And then use this linear approximation to complete this table. So first let's find our tangent line. If f of x equals 1 plus 2 sine x, our first step would be to find the slope of the tangent line. And the slope is going to be the derivative of f of x. So we have 0 and then 2 cosine x. Now this is our generic slope at any point on the curve, but we want the tangent line at the point 0, 1. So our slope at x equals 0 is going to be 2 times the cosine of 0. We know that the cosine of 0 is 1, so this is 2 times 1, which gives us then a slope of 2. Now using our point slope form of the equation with the point 0, 1 and slope 2, we have y minus 1 equals 2 times the quantity x minus 0. So our equation of our tangent line is y equals 2x. We'll add 1, so plus 1. That makes This is our tangent line, and they asked us to call it t of x. So t of x equals 2x plus 1. Now we're going to use this equation to fill in these cells, and then we'll use this equation to fill in these cells. And they should be very close in value. Let's fill in our f of x first. When we put negative 0.1 into f of x, we get 0.8003. And when we put negative 0.01 into f of x, we get 0.9800. When we put 0 in, we get 1. When we put 0.01 in for x, we get 1.0199997. And when we put 0.1 in to our function, we get 1.1997. Now let's calculate our value of our tangent line at each of these x values. When we put negative 0.1 into our tangent line equation, we get 0.8. When we put negative 0.01 into our tangent line equation, we get 0.98. When we put 0 in, we get 1, and then 1.02 and 1.2. So you can see from our table that the values, as we get closer and closer to our point of tangency, our values for the function and the tangent line are almost the same. Now real quick, let's look at using our differential definition. Our differential, we're asked to find the differential dy if y equals sine 3x. So our differential is defined to be f prime of x dx. So using that definition, we see that dy is equal to the derivative of sine is cosine, and then the derivative of what's inside. So the derivative of sine is cosine 3x, and then times the derivative of what's inside, so that would be this part of the function. So that's 3, and then times dx. So our dy is equal to 3 cosine 3x dx. One more. Find dy if y equals the quantity x squared plus 1 raised to the 1/2. So by definition, we just need to find the derivative of this expression. So dy is equal to 1/2 that quantity x squared plus 1 to the negative 1/2 times the derivative of the inside stuff, which is 2x, times dx. We simplify this a little bit. We can cancel the 2's here and write this as a radical in the denominator. So we have dy equals x over the square root of x squared plus 1 times dx.